All right, by request, section 10.4, number 49, we're asked to find the length of the curve. R is equal to cosine to the fourth power of, let's see, theta over 4. And we happen to not know initially what that curve looks like. They tell us that we can use a graphing device, so I will go ahead and use Desmos. And I just graphed this here from 0 to 2 pi, but you could see that if I continued on, it would actually graph out the entire curve. So I'm going to just integrate from 0 to 2 pi and double that up. But that is the actual curve that we're interested in. So the arc length will be twice the integral from theta equals 0 to theta equals 2 pi of, let's see, arc length, right? ds. Well, ds in this case, I'll do this as an aside. Maybe I'll keep that screen visible there. But ds is going to be the square root of r squared plus r prime squared d theta. So I want to find out what is r squared. Actually, I could technically just find out what is the square root of r squared plus r prime squared. And then we can throw that inside the integral there, right? So here we go. R squared, let's see, the square root of r squared is cosine to the eighth theta over 4 plus. Now, r prime is going to be a bit of a mess. It's a long chain rule. Let's see, derivative of cosine to the fourth is 4 times cosine cubed, first of all. But then, now that we've taken the derivative of the cosine to the fourth, we have to take the derivative of the cosine, which is a negative. There's a little negative sign there. Sorry about that. Sine of theta over 4. But now that we've taken the derivative of the cosine, we have to take the derivative of the interior, which would be 1/4. So I'll divide that by 4. And in the end, you're going to square that. So it's a bit of a mess. It looks terrible, but actually cleans up beautifully. Let's go ahead and just simplify that statement. It's cosine to the eighth power of theta over 4. Let's see, plus, because 4 over 4 cancels in negative squares, so that becomes just a positive 1. And we have a cosine to the sixth when you square it over of theta over 4, and a sine squared of theta over 4. Both those terms have a cosine to the sixth in common. I'll take the square root of cosine to the sixth. Technically speaking, when you take the square root, the even root of an even power should be the absolute value, technically. So it should be the absolute value of cosine cubed of theta over 4. And then you're left with a cosine squared of theta over 4 plus sine squared of theta over 4. Now, the way I've chosen to integrate this, from 0 to 2 pi, that cosine of theta over 4 from 0 to 2 pi is always positive. It actually takes 4 times as long to go through a full rotation of the cosine curve. So instead of taking from 0 to 2 pi to get that done, it takes twice as long. So it's, or I'm sorry, 4 times as long. So it's 0 to 8 pi. So here is 4 pi. And here, my friends, is 2 pi. So from 0 to 2 pi, that cosine is always positive. So we do not actually need those absolute values. So I can say, well, this is equal to just the cosine cubed of theta over 4. And square root of cosine squared plus sine squared of the same angles is just 1. And now that I know that that's what ds is equal to, I can substitute that back in. It's actually not what ds is equal to, but it's close. This is 2 times the integral theta equals 0 to theta equals 2 pi. And this will be cosine cubed. I think most people at this point, once they get here, I think they're okay. I think getting to that point is the tough part. And then you just have to do a little bit of trig integration here. So this is going to be 2 integral theta equals 0 to theta equals 2 pi of cosine squared of theta over 4 times the cosine of theta over 4 d theta. And I'm going to trade out that cosine squared for a 1 minus sine squared. Keep my handwriting a little bit better. Geez. theta equals 0 to theta equals 2 pi. We have a group here of 1 minus the sine squared of theta over 4 times the cosine of theta over 4. To be honest with you, I dislike these angles in here, so I'm going to just do a u sub here. I'll let u equal, it's not necessary, it's just in my way, so it bothers me. Let u equal theta over 4, which implies that du is equal to 1/4 d theta, or in other words, d theta will be traded out for 4 times du. So when I do that substitution, I'll get 8 integral. When theta is 0, u is 0. When theta is 2 pi, u is pi over 2. And I'm going to actually distribute that cosine through. Remember, that's now a cosine of u, and that's now a sine squared of u. So I'm going to have an integral of cosine of u minus the cosine of u sine squared of u du. Now, the first one's not going to be too terrible. That's just 8 times the sine of u evaluated from 0 to pi over 2. The second one, on the other hand, minus 8 times the integral from u equals 0 to u equals pi over 2 is a little extra work, right? So cosine of u sine squared of u du. And I'm going to go ahead and let x equal the sine so that dx steals out the cosine. So I'm going to let, we haven't used the variable x here, so let x equal sine of u so that du, or dx, sorry, will steal away a cosine of u du. So let's see, this is 8 times sine of pi over 2, which is 1, minus sine of 0, which is 0, minus 8. This will be the integral. When u is equal to 0, x is equal to 0. When u is equal to pi over 2, x is equal to 1. And let's see, x squared dx, that's it. It's very nice, actually. So this is going to be 8 minus 8 times, that'll be an x cubed over 3 from 0 to 1. So that's just 8 minus 8 thirds, which is 8 thirds. 324 minus 8 is 16 thirds. All right. And I think that's absolutely correct. I think that we did everything correct there.